Yeah, take it down. I'll give you the next one. Yeah, have you taken it down?
Yes, sir.
Okay, I'll rub it off. I just want, tell me, in your calorimetry quiz, calorimetry home quiz, how many questions are there? 17 questions, huh? Okay. The sixth one is a graph question. Is the sixth one a graph question? Yeah. I can't hear you. Can you put your mic somewhere near? Where is it?
Yes, sir. Six questions.
Yes, sir.
Yeah. Okay, okay. So, these are the answers. Now you can drop this question, okay? Yeah, have you taken this?
Yes, sir.
I'm writing the next one. KTG1 home quiz. P1 is approximately equal to P hydrogen, 1.25 10 power 6 Pascal. P2 is
26.
3 rho naught by 2.
Thank you, sir. तो zoom कर लो. सर ऊपर करो.
Yeah, have you taken this?
Yes, sir. ये देखियो ये.
Yeah, have you finished taking this?
Yes, sir.
Okay, slight change here. This is 23rd, this is 24th. And 22nd I'm writing here. Yeah, 21, 23, 24, 22, okay. Yeah, can I rub this off?
Yes, sir.
First 16 questions, shall I rub off?
Yes, sir. Yes, sir. शुरू से करें.
Yeah, can I rub off this, the right side of the board?
Yes, sir.
Have you taken the first 12 questions?
Yes, sir.
Yeah. Have you written this FLT? Can I rub this off? So there I have given you answers to all home quizzes. Yeah. Have you taken the conduction home quiz answers? The red one. Let's start with radiation now. I want to complete that. Yeah. Have you taken all this? See, we are starting off with radiation. The first thing we do in radiation is Stephen's law. Stephen's law says that the emissive power equals epsilon sigma A T power 4. Here, this is called emissive power. This is called emissivity. This is Stephen's constant. This is surface area. This is the absolute temperature of the body. Every body emits radiation. Even you and I emit radiation. But does it mean that in a dark room we'll be visible to each other? And if not, why are we saying we emit radiation? Our radiation is not in the visible range. The visible range is from 360 nanometer to 760 nanometer. We emit radiation in infrared range. That's why the BSF uses night vision binoculars to man the borders. Anybody trying to act smart crossing the borders emits a infrared silhouette. All they have to do is pull the trigger. So you can make out who is there. Because everybody emits radiation. So this is emissive power, electromagnetic energy emitted per unit time. Emissivity is something like efficiency. We will see what it is. Its value ranges from 0 to 1. The best one is the black body has the best emissivity. Black body emissivity is taken as 1. Anything will have an emissivity between 0 and 1. Sigma is a universal constant called Stephen's constant. Its values are available in a fixed book. A is the area, surface area. T is absolute temperature. In Kelvin scale, you will have to mention the temperature. So anything emits radiation like that. This is one of the laws, so to say. Let's see another idea. The next idea I'm talking about is a black body. Well, you might say this is a black body. It looks black. But in terms of physics, this is not black body because this is black, you are saying, because any visible color, all visible colors it absorbs. It doesn't emit anything for you. So this absence of color you call black. but maybe this is emitting, and rather it is emitting infrared rays or ultraviolet. So you cannot make it out. So in terms of physics, this is not a black body. In terms of physics, something is black if it absorbs all radiations, including infrared, ultraviolet, the whole electromagnetic spectrum, not just visible. So what is a black body in terms of physics? What we usually call black body may not be black in other range. In terms of physics, we design a black body like this. We have a shell and we keep a small hole there and we draw a beak-like thing here. So what happens? This is the shell through which there is a hole. Any radiation which enters this will go on either side of the beak. It will always get reflected eternally and it will never come out. It will go on getting reflected, never coming out, and since it never comes out, it is called as gone. If you try to see something, what goes in never comes back. That's the idea. This is called a black body in terms of physics. See, if the beak was not there, suppose it was only like this, a radiation which goes in like that might come out like this. Then it won't be black because it is emitting something. This is the idea of a black body. It absorbs anything which is put on it. Yeah, is this fine? Then we have another idea. So I'm rubbing this off. Consider a body. If electromagnetic radiation is incident on it, it can get reflected, it can get absorbed, it can get transmitted. We say A plus R plus T is constant, or rather zero. A is called absorptivity. It is the ratio of energy absorbed upon energy incident. So for a black body, absorptivity is taken as 1. That's what is a black body. It absorbs all the energy incident on it. This is absorptivity. What do you think is reflectivity R? By the same logic. Energy reflected upon energy incident. Likewise, what is transmittivity? Energy transmitted upon energy incident. Now, if reflectivity is 1, that's an ideal mirror. And if transmittivity is 1, that is ideally transparent body. Even your spectacles, transmittivity is not 1, because you might feel that all the light is going in your specs, but your specs reflect light. Even from here I can see some of your specs are reflecting some tube light or some kind of a light. So some of it is coming into my eyes. So you don't get all the share, some of it is getting reflected. So transmittivity is not 1. So anyway, the sum of all these is always 0. I'm sorry, not 0, it will be, this will be 1, okay? So it can have any value from 0 to 1. Every body will have some combination of this. But if you have A equal to 1 black body, R equal to 1 ideal mirror, T equal to 1 ideally transparent. Having said that, now I am saying something else which is called the Kirchhoff's law of radiation. Can I rub this off? For similar bodies, when I am saying similar bodies, I mean same area and having same temperature. The emissive power of a body to its absorptivity equals the emissive power of a black body to the absorptivity of a black body. This is called as Kirchhoff's law. This is for any general body, this is for a black body. But we know that absorptivity of a black body is 1. So what we get is emissive power of a body equals absorptivity of a body into emissive power of a black body. For a general body, this is epsilon sigma A T power 4. This is for a body. This is the A body. And this is for a black body. Epsilon sigma A T power 4. Now for a black body, as I told you earlier, emissivity is 1. Now A and temperature are same on both sides. Sigma is anyway same. So what do we get? We are getting emissivity of a body equals absorptivity of a body. Now this statement means good absorbers are good emitters. Now as a general statement it's okay to say, like in a class you are expected to absorb and in a test you are expected to emit. So if you absorb well you can emit well, but what does it mean in terms of physics? That's what we want to understand. Now look at an experiment I talk about. If you have a black body and you go on heating it, temperature, let's say more than 1000, you go on, then what happens after some time, white light comes out of it. Now there is nothing inside that, there is no filament, nothing. And white light, the black body will emit white light. It becomes self-luminous. I'm not justifying why it happens, I'm just telling you what happens. Why it happens is the beginning of quantum physics. Just to say that the oscillators inside the black body surface give white light. Why they do so, we are not getting into it, they do so. So this can tell you that black body emits white light. Another statement which sounds contradictory, we say in physics, sun is a black body. By the same logic, we say sun is so hot, it's emitting white light because to begin with, only a black body can emit white light. Sun is emitting white light, so it's a black body. Now, you have not experienced this, but I can give you a feel of roughly. For example, if an iron nail, if you heat it, what is the color it takes? Red. You talk about red hot. Around 800 degrees centigrade, the iron nail becomes red hot or iron becomes red hot. That's what a blacksmith can hit and forge. For example, you can create tools with forging. That's called the forging process. Iron becomes red hot. Then if you heat it further, 3000 degrees centigrade, iron looks like orange ice cream. It is luminous and takes on the color of orange, and it can be poured into caskets and you can create any shape. For example, statues are created like that, or a machine is created like that, engine is created like that. You can pour molten iron into any shape and it will solidify like that. That happens 3000 degrees centigrade. So what I'm trying to say is iron, which is black and grey in color to begin with, becomes red and then becomes yellow, and if it go on, finally it will become white. That's the idea we're talking about. Good absorbers are good emitters. So in a way, absorptivity, emissivity in terms of value are one and the same. Although conceptually they are different ideas, but they take on the same value. So finally, I show you one more thing. Have you taken this?
Excuse me, sir.
Yeah.
So what about tube lights?
Tube lights are not, that is a different phenomena. Electrons are emitting. That is not because of temperature. That's a different phenomena altogether. We are not talking about that. Okay? That way you can ask, what about candle, what about tube light, what about bulb? That's electricity. We are talking about just because of temperature, when something gives radiation, how is that? So, can I rub this off?
Sir?
Yeah.
Sir, even in the bulbs, when due to heating the filament grows white.
Yeah, you can say that. You can say that part. That's right. That's right. Bulb is happening by heating. That is incandescent lamp. Yes, it does happen. Rather, the tungsten filament bulb, its temperature is 3000 degrees centigrade, and that's why we have to keep it in an inert atmosphere. You vacuum it and put something else. Otherwise, it will have combustion. If it's an oxygen atmosphere, it will have combustion and you won't get the filament. The filament will burn off. But you make the filament glow because, yeah, that's exactly the idea we're talking about. No, I'm saying black body emits, but other bodies can also emit. You don't have to have, okay, it doesn't have to be a black body. A black body emits the best. Other bodies may emit somewhat less. That is what is measured by emissivity. Emissivity is like the efficiency factor. Just one more idea, you can absorb this also and then ask some questions if you want. If you heat a body and if you plot a graph between E lambda and lambda. E lambda is called spectral emissive power. This is the energy emitted per unit for a given wavelength. That's called, see, if you talk about just energy emitted, that's called emissive power. But if you talk for a given wavelength, that is called spectral emissive power. If you plot a graph using a spectrophotometer, you can take the radiation from any substance and send it to a spectrophotometer, which can find out what is the wavelength coming and what is the radiation intensity. So you get a graph like this, a mountain like this, which means, yeah.
So will you please repeat the definition of spectral emissive power?
Spectral emissive power is emissive power for a given wavelength. What is emissive power? Electromagnetic energy emitted per unit time is emissive power. And spectral emissive power means for a given wavelength. We also call it like this. It is the emissive power. We can write like that. dE by d lambda. Suppose you have a lambda here and a little away you have a lambda plus d lambda. This area represents dE by d lambda or the E lambda. If you take the total area under the graph, the total area equals integral E lambda d lambda, which is nothing but integral dE by d lambda times d lambda, which is nothing but integral dE, which is nothing but the emissive power. The area under the graph gives you emissive power. Yeah, is that okay? Now what happens is, if you heat this body, then you got a mountain like that. See, this mountain also has a peak at a particular point. That's called lambda m. And this is the temperature T at which this peak is formed. Now if you heat the body, you get again all the wavelengths become more and the mountain shifts like this. The peak of the mountain shifts to the left. This is temperature T dash. It is lambda m dash. What is seen is lambda m times T happens to be a constant. This is called as Wien's displacement law. Okay? Now this is a Wien's constant. It will be a constant for it's a constant for all bodies. The value will be given to you in a question if required. You can always find the values in the physics book, Stephen's constant and Wien's constant. So the peak shifts to the left and the mountain becomes larger. Every wavelength will start giving more energy, but the topper or the